I've gotten a couple of requests to talk some more about partial derivatives, uh, and my emphasis here is going to be on economic interpretation. But hopefully, what I'll be able to do in this video is give you a little bit more intuition about what a partial derivative is and how to do it by looking at some examples. So before we do a partial derivative, let's just do a normal derivative of a function with one variable and make sure we understand what we're doing there. And then let's go on and look at a little bit more complicated function and do a partial derivative. Now, first, just looking at a function of one variable. For example, we could look at, say, y equals, I don't know, 3x to the fourth power plus 6x to the third power minus 2x to the 2x squared plus 4x minus 15, for example. When you take a derivative, the rule is that if you have multiple terms that are added together in a function, then to take the derivative of the whole function, all you have to do is take the derivative of each individual term separately and then add what you get for those separate terms. So if we were to take the derivative of this whole thing, you just take the derivative of the first polynomial term here, and the procedure is take the exponent and multiply the entire equation by it, and then subtract 1 from that exponent, and that's your derivative. So for this term, we would get 4 times 3x. Let me change into a color that's a little bit more easy to see. 4 times 3x, and subtract 1 from that 4, so 4 times 3x cubed. And this will be familiar to most of you. And let's just carry on and do the rest. 3 times 6x will give us 18x. Right, and again, we can collect those two, 3 times 4, and make it into a 12. So let me go ahead and do that, so I'm not going to confuse anybody. 18x, subtract 1 from the third power, and you get the second power. Minus 2 times 2 is 4x. Subtract 1 from the 2, and you get 4x to the first, plus 4 times x. So this is really 4 times x to the first. 1 times 4 leaves the 4. Subtract 1 from that exponent, and you get x to the 0 power. But x to the 0 power is just 1, so we don't have to write that down. Typically we won't. And then minus 15, the constant, the derivative is just 0. Now, why is the derivative just 0? Well, let's look at a slightly simpler function that will be slightly more obvious, and hopefully you'll see why the derivative of that is 0. Let's just look at a function of a parabola, function with a squared term in it. So let's say we had one that was like 3x squared plus 4x minus 15. Let's put that 15 there again. Now, this is a parabola. So let me just graph a random looking parabola over here. And this function is going to look something like this. It's going to be an upward sloping parabola, something kind of like this. And when we take the derivative of a function, remember what we're really doing when we take that derivative. Here's the symbol we'll usually use for a derivative, dy dx. And the d's stand for change in. So dy dx, what we're really talking about here is change in y divided by change in x. In other words, rise over run. Right? Rise over run, which is slope. Change in y is rise. change in x, is run. So when we're taking the derivative, this symbol here is meant to remind us what we're really doing is we're trying to find the slope of this function, which is a parabola, at each point. And so as we see, sometimes the slope is negative. Down here it's 0. Over here it's positive. And so when we take the derivative, let's just go through the process here again. 2 times 3 is 6x, and the 2 minus 1 is to the first power. So the derivative will be 6x plus the derivative of 4x is just 4. The derivative of the minus 15 is just 0. That minus 15 does not influence the derivative or the slope in any way. That's what we're saying. Why not? Well, because in this function, and it turns out for any function, if there's just a number that is added or subtracted on at the end, all that's going to do is change the value of the y. It adds or subtracts from the y more or less directly, but it doesn't impact the slope. So if this number 15 wasn't even there, then the parabola would look something like this. I did a pretty poor job doing that, but what I was trying to do here is just shift this parabola up by 15. Parallel, everything parallel, shift it up by 15. And so what's that going to do? Well, at every point that we could look at, say x equals minus 5 or something like that, then the slope of the parabola at those 2 points is going to be identical, whether or not we subtract 15 on the end or not. So when we take the derivative, that minus 15 just goes away. So I'm explaining to you to make sure you understand a regular derivative first before we get into partial derivatives. If you don't understand this, a partial derivative will fly right over your head. So now let's talk about partial derivatives. So what we've done here, you could call, if you want, just a derivative of a single variable with a single variable. And this is single variable calculus. And when we do a derivative of a function like this, we use the letter dy dx. Now, this is related to the Greek letter delta, which means change in other contexts. So we could kind of write delta y, delta x, and we would be talking about a similar operation. But with a derivative, we're talking about infinitely small changes in y and x. Usually when we use delta y, delta x, we're talking about a certain change, like a change of y of 3 and a change of x of 1, for example. But let's go ahead and let's start contrasting what we do when we take a partial derivative. So here we are in the world of a partial derivative now. Now, a partial derivative, we usually use this kind of term when we're talking about multivariate calculus, or a function that has more than just a y and an x. So here's a function we might look at. So let's look at a polynomial function with some additive terms in here to start with. So y equals, I'll use a's and b's here instead of x's. So y equals 4a cubed times b to the 4th plus, let's say 6a cubed times b squared minus, and I'll just add another couple of terms here real quickly, minus 5a squared b plus, and let's put on a number at the end, like 15. So our rule for taking derivatives is basically the same, except we're going to add one little caveat. What we're doing now is when we take the derivative, we're going to have two different possible derivatives that we could take here. We could ask the question, let's go back up here to contrast. Here the derivative asks the question, when x changes, how much does y change? In other words, what's the slope? What's the impact on y for a change in x? And that changes at different points along this parabola, or whatever the function would be. Now here with the partial derivative, we could ask two kind of related questions. Question number one could be, I'm going to use a curly d. This is just the convention, lowercase Greek delta, or a d with a kind of a curly top on it. We could ask the question, what is the change in y for a change in a? Because there are two variables here, a and b. So we could do that derivative, and what we'd be doing is finding the slope of y, the rate of change in y, when we change the a variable everywhere in this equation. Let's do that derivative. And so this is a partial derivative. And here's the rule. Here's the one extra thing to keep in mind. When you're taking a partial derivative, everything that does not involve the a, you treat just like a constant. Let me repeat that again. Everything that does, when you take the derivative with respect to a, unless there's an a involved, you treat it just like a constant. So here's a constant. Here's a, here's a a, here's a a. And let me add one more term at the very end. I apologize for doing this to you. Let me add another term, plus 3b. Okay. Notice, let me try to explain why I did this. This term 15 doesn't have an a, so we're going to treat it like a constant. This term is 3b. It doesn't have an a, so we treat it just like a constant, just like we would the number 15. Here we treat this b just like we do the number 5. They are both treated as constants when we're taking a derivative with respect to a. So let's, without further ado, let's do this. The 4 and the b to the 4th power we treat like constants. Since they're both multiplied by this a cubed terms, we just write them down. 4 times b to the 4th times, now we do the derivative of the a cubed. And that's going to be 3a squared. And now that we're done with that, we could collect these two things that really are constants. The 3 and the 4, 3 times 4 is 12. Right? So we can rewrite that as 12 b to the 4th a squared. Now let's look at the second term and take the derivative, or the partial derivative with respect to a. The 6 and the b squared we treat just like they're constants because they don't affect the slope with respect to a. So we just write them down. 6b squared. Now we take the derivative of the a cubed term again. Well, it's the same thing we did before. It's 3a squared. And now we can collect the 3 and the 6. 3 times 6 is 18. So here we go. 18b squared a squared. Now we look at this next term. 5a squared b. The 5b we treat as a constant. So 5 and the b. Now we take the derivative of the a squared, which is just 2a, plus the derivative of the 15 with respect to a, it's 0, so we leave it alone. The derivative of the 3b, since there's no a in it, we treat it like a constant, and that derivative is also going to be 0. So we're done. Except for we can clean this last term up a little bit. 2 times 5 is 10, and b a, or ab, that would be the same thing. So here is the derivative with respect to a is 12b to the 4th times a squared plus 18b squared a squared plus 10ba is the derivative with respect to a. Now, what this will tell you is if we plug in values of b and a here, it'll tell us at what rate y is going up as we increase the value of a by 1. For example, we could plug in the values a equals 1 and b equals 1 into this function, and we'll just get 12 times 1 to the 4th, 1 squared, 1, etc. And what we'll get is just 12 plus 18 plus 10, and the value there would be 40. What that tells us is, at that point where a equals 1 and b equals 1, as we increase a by a tiny bit, the value of y goes up at the rate of 40. 40 times as much as we're changing a. Very steep. So now let's take the other possible partial derivative we could do here. What's the slope of y? How fast does y change as we change b? Pause the video and do this yourself to see if you can do it, and then come back and I'll show you the answer. Okay, so hopefully you did. I'll give you one last chance. Okay, so now we're going to look at this function here. Let me erase all these little underlines that I had before so I can make some new underlines. Now we're going to treat everything that doesn't have a b in it just like it's a constant, just like it's a number, and take the derivative of the things that have b in them. So let's look at the first term here, 4a cubed b to the 4th. We just write down 4a cubed to treat it just like it's the number 4. And then we take the derivative of the b to the 4th part, which will be 4b cubed. And then we can clean that up. 4 times 4 is 16. A cubed, b cubed. Plus the next term here, 6a cubed b squared. The 6a cubed, we just write it down because that's a constant when we are taking a derivative with b. So take the derivative of b squared, 2b. Now we can collect the 2 times the 6, 12. A cubed b plus the next term, 5a squared. We treat like a constant because we're not looking at a slope with respect to a, we're looking at the slope with respect to b. And now we take the derivative of the b part, which is just going to be the number 1. Because it's b to the 1st, we multiply everything by 1. That doesn't change anything. And then we subtract 1 from the exponent, that's b to the 0. So the derivative is just 5a squared. Very simple in that case. So let's write it down on our other line where we're writing down our cleaned up version. What's the derivative of 15 with respect to b? Well, it's just 0. There's no b in there. But then this last term, there's a b, so we have to take the derivative of that just like we would normally. We write down the 3 because it doesn't have a b, but then take the derivative of the b, which again just gives us the number 1. So plus 3, and here's our finished derivative here, which tells us how does this function change? How fast does the y function change as we change the b variable at each point along this surface? Now this is going to be a 3-dimensional surface here since we have 2 input variables and 1 output variable here. And so, for example, if we do what we did before with this one, plug in a and b equal 1, let's see in which direction is it steeper as we increase a or b. Well, if a and b are both 1, then that's just going to be 1 cubed, 1 cubed, 1 cubed, 1, 1. So we'd be adding 16 plus 12 plus 5 plus 3, which is 27, 35. So the slope at a equals 1, b equals 1, if we just looked at that one example point, why that point? Because it's easy to calculate. The slope would be 35 in the y direction. in the direction as we increase b, right? As b increases. Here, when a equals 1 and b equals 1, what we would find here is that when we added that up, we got 40. The slope would equal 40 as a increases. So, what's the point? Well, the point would be, suppose you could either change in this function, suppose you already had a equals 1 and b equals 1, whatever the context this is. Maybe this is a production function, and this tells you how many cars you can produce, depending on how many workers you have and how many machines you have. A workers, B machines. If you had one worker and one machine, how fast will your production increase if you increase the number of A workers? You'll get 40 more output, is what that slope would tell you. But if you increase the number of machines, accidentally erased that. If you increase the number of machines, derivative of b, how does y change when we change b? The slope is not as big. You'd only be increasing your output at a slope at a rate of 35 at that point as you increase the number of machines a little bit. So hopefully that helps you out. Now let me do one more problem here, because many times in economics, especially microeconomics, you'll have functions that look like this. Y equals a to the 0.4, b to the 0.07, say. And with these fractional exponents, maybe things look a little bit weirder to you. So let's take a derivative of this function, or the two partial derivatives, just to get a handle on that one more time. So let's do dy. It should be actually kind of curly dy, if you're really going to be careful with looking like your notation is proper for a math class. Then dy dA, or derivative, you just write down the b term the same way. It's not going to change, b to the 0.7. Then do the derivative of the a term, since these two are multiplied. So it's going to be times 0.4 times a, subtract 1 from that exponent. 0.4 minus 1 is negative 0.6. And then we could clean that up a little bit to just make it look a little bit easier on the eyes. So 0.4 times b to the 0.7 times a to the negative 0.6. And that's going to be different from the slope in the b direction. So what's the partial derivative of y when we change b? Slope in the b direction. We write down the a part without changing it, and then we take the derivative of the b section. So times 0.7, multiply by the exponent, subtract 1 from the exponent. 0.7 minus 1 is negative 0.3. And again, we could just rearrange those terms. Normally we'll put the constant out in front, a to the 0.4, b to the minus 0.3. And there you have it. That's the idea behind partial derivatives. Now we will look at this later, if you want to look at my other videos, look at the videos where we're talking about marginal rate of substitution, and you'll get a little bit more intuition, and you'll see more examples of partial derivatives. You'll get a better intuition looking at some graphs about what these partial derivatives actually can mean on a graph and in the real world. So if you have any questions, please let me know in the comment section below, or feel free to contact me by email.